lymph node, but you'll see the pictures of what that looks like inside there. So lymph nodes, this is our main lymphoid organ, and we have hundreds of them in our body, okay? They're embedded into our connective tissue. We basically have them all scattered throughout our whole body, but you do have more of a concentration of them in certain parts, okay? The inguinal areas, which is really in the groin, the axillary area, which is in your armpit, and the cervical area, which is in your neck. It's like people are around the United States, but we have a lot more people in New York City and Chicago and Los Angeles. But there's people all over the place. So we have lymph nodes all over the place. We just have a lot more in these three areas here. Okay? So this is showing you the same thing. So we just have a lot more lymph nodes in the axillary area, we have a lot in the neck area, and we have a whole lot in the inguinal area. But keep in mind, we have lymph nodes throughout the whole body. Okay? So this is kind of showing you where they drain to. And you know, so here's the breast. So if there's, let's say, cancer that's in the breast, okay, they're going to go to the most of the cancer cells will go towards the axillary nodes. So they're going to, if they're going to check to see if the breast cancer spread, they want to check the lymph nodes that are located in the axillary artery. I'm sorry, the axillary lymph nodes. If they see, because that's where most of it is going to end up going. So you just, you know, if they do see that it's over there, then it becomes a different stage of cancer. If it's not there, then the cancer stayed at the breast. It didn't spread anywhere else, and then you're at a different stage, an earlier stage cancer. And that's how they stage things. You've heard of stage 1 or stage 2 breast cancer or any kind of cancer. That's where they're talking about how far did the cancer go to. Can we see cancer cells that are located in the lymph nodes? If you can't, then it stayed in a localized area like the breast. Okay? So the functions of the lymph nodes is filtration. Okay? Just the way we talked about having the spider webs in there so that fluid can get through, but it's going to sequester the bacteria or viruses or cancer cells. All right? It's an immune system that's going to monitor for antigens, and if they see a foreign antigen there, they're going to mount an attack and destroy it. All right? So that it doesn't go further. Okay? So the anatomy of the lymph node, they're, like I said, they're about the size, when there's nothing in there in terms of like bacteria, so it's not infected, there's no infection going on there. They're about the size of a pea, okay? Maybe a little bit smaller, but they're about that size. Or an eraser head is a good example of the size of that. But they do get big. I mean, I've seen them just shy of a marble, okay? So I mean, they do get big in a sense like that. So they are bean-shaped. There's a fibrous capsule around it trying to keep everything together. Inside, we have these things called trabeculae, which is basically the webbing that you're seeing in there. And that's going to put that in compartments, okay? And then you have a cortex and a medulla, okay? The cortex and the lymph node, basically they're follicles with the germinal centers, and we have the dividing B cells that occur in there. They're encapsulated. The dendritic cells nearly encapsulate each of the follicles. So what I'm saying, the follicles are these balls that are in here. Each one of those is a follicle. So around there, around each follicle, you're going to see a lot of dendritic cells. In the deep cortex, you're going to have more T cells. Okay. The medulla of the lymph node, you have these cords in there, medullary cords, and they kind of extend from the cortex, and that's where you're going to find B cells, T cells, and plasma cells. Okay. The lymph sinuses, we have these reticular fibers that kind of crisscross, and macrophages are going to reside in these fibers to engulf things. These crisscrossing things is developing that so-called web as I'm talking to you about. Okay? So things get stuck in there so the macrophages can grab and hold on to them and destroy what they need to do. Okay? Now, the way the lymph nodes work, well, the way they're structured is a very strategic way that it works. I'll show you what I mean by this. Things going in and out of it. All right. We have afferent lymphatic vessels and we have efferent lymphatic vessels. Okay. We have many afferent vessels, but we only got a few efferent. So let me show you what I mean. If this is going to be our lymph node, okay, we're going to have many vessels going into it. These are afferent vessels. Okay? So fluid is going to be going into here. Okay? But with the efferent vessels, we may only have one or two. Now, why is this setup like this? Why is this going to be beneficial for the function of the lymph nodes? Why do we have many afferent vessels, but only a couple of efferent vessels? Let me ask you it this way. Why is it not this way? Why is it not that we only have, I'm just giving you numbers, two afferent vessels with two efferent vessels? Why do we have many afferent and only a couple efferent, as opposed to this setup with only two efferent and I'm sorry, two afferent and two efferent? Well, the reason why is because if we just had it this way, if we had like say, a cancer cell in here and a cancer cell coming in here, they're able to actually go out the same way. In other words, 1-to-1 ratio. One cancer cell can go out here. One cancer cell can go out here. Look at this setup. You have 1, 2, 3, 4, 5, 6 cancer cells going to this lymph node, but only 2 going out. So what's going to happen is this is almost like a funnel. You're going to put all, let's say, cancer cells in here, but it's going to be, it's keeping the cancer cells sequestered in here, not allowing them to escape so fast. They could get in there very fast, but making them go out, well, it's going to try and hold them in there so that the macrophages and the lymphocytes can do the thing that they're supposed to be doing, monitoring and destroying them before they just leak out of those 2 spots. Very important concept for you to understand with this, that we have many afferent fibers, but not fibers, I'm getting nervous, but many afferent lymphatics and only a couple of efferent lymphatics. It's to keep them there, okay? So, that's what I'm saying. Afferent lymphatic vessels, many go into one lymph node. Efferent lymphatic vessels, it's usually 1 or 2 exiting the lymph node to try and sequester that, okay? You want to, because there are fewer efferent vessels, the lymph stagnates, stays in the lymph node for a longer amount of time, so that the lymphocytes and macrophages have time to carry out their protective functions so they don't escape the lymph nodes, okay? So I kind of think it's the same way as in the New York Giants stadium, right? when you get in, there's a lot of entrances going into the stadium. So they want to make sure that there's no problem people getting into the stadium. All right? But when it's time to go home, oh my God, I remember when I went to a football game with my father, and I must have been like about 8 or 9 years old. I remember going in, there wasn't much of a line going in. Going out, oh, geez, it was a ridiculous thing. Why did they set it up like that? Well, if there's, I'm just giving you numbers. If there was, let's say, 50 entrances, the exits are only going to have, let's say, maybe 25, because it's going to sequester all the people in there. This is where the concession stands are going to make their money. We're waiting in line to get out of the place. You have a little kid, 8 or 9-year-old kid. Come on, Daddy. I'm hungry. I want to get something. All right. We've got another hour to get out of this place. I'll go get a hot dog over here. Might as well get a T-shirt over here to keep them happy. You see? So they get smart about this. I don't know if they actually thought about, I don't know the person who did the architecture of these stadiums, do they keep a lymph node in mind? But that's what's happening with this. It's doing that, okay? But anyway, that's what I'm saying with this. All right, so it's kind of like the New York Giants Stadium or any kind of stadium for that matter. Okay, so this is just showing you what I kind of drew for you. We have many afferent vessels going in, but only a couple going out. It's trying to keep it all sequestered, all that fluid, and not so much the fluid, but all the bacteria, viruses, all that stuff be sequestered there so that the macrophages, the lymphocytes, can do their function, try and destroy them so they don't slip on out of the lymph node. Okay? So that's what a typical lymph node would look like. You see a lot of different lymphatic vessels going in or going out. I'll be honest, I can't tell which ones are efferent or afferent. All you see is a lot of these vessels that are connected to it, okay? But I guess you dissect, and I don't know how they did it in the medical realm, but they figured out that there was much more afferent vessels than there is efferent vessels. Okay. So like I said, clinical applications, think of cancer cells. The cancer cells, and your body always makes cancer cells. Even if you're healthy, your body's always going to be making mutated cells. But if you've got a good immune system, it's going to be able to find those mutated cells and destroy them before they go into more mitosis and making more and more of these mutated cells. So your body's always producing mutated cancer cells. So it's the job of the lymphatics and immune system that is going to, it's going to take those cancer cells into the lymph nodes. They'll proliferate there, make more of them, but it'll enter the blood and then metastasize elsewhere. So the problem is if it starts getting a lot worse, in other words, they start multiplying, the lymph nodes are not going to be able to do, there's just too many. It's like the customs. If you have, I'm just giving you numbers, 10 people that are running the customs, but yet we have 100 people that are going through customs, they're going to need more staff over there to handle that. Otherwise, the people that are bringing in guns and knives and all that stuff into the country, or drugs, that they're just not going to be able to manage that, and it's just going to take over, I would say the whole country, but it's going to be overwhelming. So that's what, and at that point, when cancer cells do that, then you got to spread, okay? Edema is a blockage of lymph flow. Some causes, and we talked about those before when we did the circulatory, compression from a tumor, surgical removal of lymph nodes, okay? But it's like we erased it up there. But it's when the fluid, that 3 liters, stays up there. But if you block any of the lymphatic vessels, then or even the lymph nodes, then you're not going to be able to get that 3 liters into the lymphatic vessels into the subclavian veins. All right, so then the fluid just sits there, and that's called edema. Right, where you take your fingers, You press down and let go, and those impressions will stay there. Okay, and that's what edema is. There's many different reasons for edema. Okay, this is edema. She had obviously her right breast removed. Okay, she probably had extensive breast cancer, and they removed a lot of the axillary axillary lymph nodes in the on the right side. So because of that, all the extra fluid, 3 liters or whatever it is, stays more in the left arm. In the arm over here, because there is no. They removed a lot of the lymphatics, so it's going to stay in the interstitial area for a longer amount of time. Now, the other thing I just want to also mention too, many of you want to go into the medical realm. If someone had their right breast removed, all right, chances are some of the lymph nodes were also removed. When you do blood pressures, you can't do it on the arm that the breast was removed, because the fluid is just going to build up too much in there when you put the cup on it, and that causes a lot of pain. And there's going to be a real long delay to get the fluid back into the system. So the rule of thumb is that if they had a right breast removed, you take the blood pressure on the opposite, the contralateral side. Likewise, if they remove the left breast, then they do it on the right side, the blood pressure. Now, if both get removed, the bilateral mastectomy, well, we have cuffs that go around the leg, around the thighs. So, so we have all those things, all right? So that's what goes on with this. So that's about edema. So this is what we call elephantitis. This is gross edema. And this is something where in the groin area, in the left inguinal lymph nodes, there was an infection going on over there, and it actually blocked any blood or any lymph flow to go into that group of lymph nodes. And you get all this fluid that's going to build up over here. And the leg starts looking like an elephant, right? So that's what's happening with that. That's a pretty gross amount of fluid that's being built up there. But that's elephantitis, because the leg looks very much like an elephant's leg, very thick like that. But we all know the biggest thing about elephantitis is this guy over here, right? The elephant guy, right? The elephant man. You've heard of the elephant man, John Merrick. He died in, I think, 1888 or so. But this is the elephant man. They had a movie about him and all. This is the elephant man. He was diagnosed, a lot of people thought it was the some sort of elephantitis, some sort of this buildup of edema. And they still have his bones over in London. I think it's London. It's in England. They looked at the bones now, like over 100 years later, and they dissected the bones. They did a lot of research on the bones and realized it wasn't edema at all, but that he had something called neurofibromatosis. Okay, that's what he ended up having. Basically, what neurofibromatosis is remember we talked about in AMP1, the myelin that's on the nerves. Well, if the myelin becomes cancerous, it starts building up bigger and bigger. So you got something that looks like this. Right? If this is a nerve over here, and then you're going to have the myelin that's over here, right? Schwann cells and stuff. Well, if the myelin becomes cancerous, it gets bigger. Well, sometimes this gets really big and it starts growing in a haphazard way. And when it does, you get this, okay? And that's what he ended up having, okay? Now, what does neurofibromatosis look like in today's day and age? We do see it, and you get these bumps all over the body. He just had a very exaggerated amount, but it's this, and it looks like a lot of warts. So that's extensive neurofibromomas, okay? All right, so that's what that is. All right, so the spleen, okay? This is our largest lymphoid organ. It's located in the upper left quadrant, right? The upper right quadrant is our liver. The upper left quadrant is going to be our spleen, okay? The blood supplies are splenic artery and nerve, or splenic artery and vein, and they will enter and exit the hilus, okay? The hilus is, when you take the spleen, if it's shaped like this sideways, the hilus is this little indentation going in, okay? So it actually will go in there, so the afferent is there, and the efferent is here. So it's kind of, you know, it's not like this, it's more, it goes in that way, and the fluid will go out that way. It's all entering and exiting the hilus area of the spleen. Okay? So functions is the site of lymphocyte proliferation. We're going to have the surveillance going on there, response. So it's a gigantic lymph node if you think of it that way. Architecture is a little bit different though. This is also the site of fetal red blood synthesis. Okay, the liver and spleen in the fetus are being produced by the liver and spleen. When the child is born, then it goes. We talked about this. Then it comes from the legs of the bone marrow in the legs, and then in adults, it's usually the skull, ribs, and vertebrae that the red blood cells are coming from. And also stores a lot of blood platelets. Okay. If someone ruptures the spleen, let's say they're doing in football or soccer, gets kicked, something, morbilliaplax and something like that, there's a lot of blood inside the spleen. You don't want to hear a splenic rupture because they'll be losing a lot of blood. There's a lot of storage of blood going on. Okay? So the anatomy of the spleen, there's a capsule around it to hold everything together. The trabeculae are going to be, and that's that spider web that we're talking about in the lymph nodes. Well, this is no exception. The spleen also has this spider web going on, the trabeculae. We have many red blood cells there with the lymphocytes and macrophages. Then we have something called a white pulp and red pulp. And the weird thing about this is that when we look under a microscope about this, the red pulp appears white and the white pulp appears red. Okay? So the white pulp is where the lymphocytes are all located. The red pulp is these worn out red blood cells. If we look under microscopes and it's already dried out, the colors are different, the way they stain and stuff. So what we're looking at over here, all right, when you take a section of the spleen, all this white area is the red pulp. But you have these reddish areas, those are their white pulp. So it's kind of the opposite. Okay? And again, what I was trying to draw you over here about the afferent and efferent of the spleen, they're showing you over here. So the splenic artery goes this way, the splenic vein comes out the same area, the hilus of the spleen. Okay? All right, the thymus. We talked about this with endocrinology also. The thymus is located just anterior to the heart. Okay? It's overlying part of the heart. It grows until about adolescence. This thymus is going to release hormones called thymosins. Thymosins is going to mature lymphocytes to become T cells. That's where the T comes from, the thymus. Now, what happens in adults is that we don't need the thymus anymore because all the T cells are mature. So now they have a nucleus, so they will go through mitosis and make more and more and more. They don't need the thymus to be making mature ones because the mitosis will just happen with all the mature cells. But as a child or as an adolescent, you've got to build a lot of them. It takes some time to do that. So what I'm trying to say is, in a child, the thymus gland is a rather large organ. But to a 50-year-old, it's virtually unidentifiable. It's not there. It might be just a little sliver, but it's not working in an adult. Okay, and there's very little to see on it. Okay. The anatomy of this, there's no reticular fibers there. The trabeculae has these, there's a lobule in there and has a cortex and medulla, similar to what we saw with the lymph nodes. The cortex has numerous lymphocytes. Medulla, they have lymphocytes, but there's less there. Okay? So it's kind of showing you, again, here's where the thymus is located on top of the, or anterior to the heart itself. And again, you can see these lobules. So this is the thymus, this whole thing is the thymus, but we're going to take, there's a lobule here, a lobule here, and you're going to have an inner medulla of the lobule, and then you have the outer cortex of the lobule. Okay? So in summary, this is a great picture. Put your pencils down and just look over here. This is a great picture to show you how the whole thing comes together. So just follow me on this. Let me use this broom. I'm sorry for confusing the broom. It was kind of, I got to look for a point. But what's happening here is this. So we have the heart that's going to pump blood into your arterial circulation. All right, now remember, oncotic pressure, you're going to have the hydrostatic pressure and osmotic pressure that's going to be pushing out 30 liters of fluid, and then 27 liters comes back. The 3 liters is going to stay in the interstitial area. Okay, so 30 liters goes into the interstitial area, 27 liters goes back into the venous system. Okay, but the other 3 liters are going to go into the lymphatic system. Customs is going to go on to try and remove whatever it needs to do, bacteria, viruses, cancer cells. Okay, and that fluid that's going to be cleansed now from all that bacteria is then going to go back into the venous system. Okay, so that's what goes on over here. All right, we also have in the small intestines, we have modified lymphatics called lacteals, that when the small intestines is able to break up the fats that you eat, they're just too damn big to get into the bloodstream. So the lymphatics are going to be able to take on these bigger structures, and these lymphatics are called lacteals that are able to absorb the fats, be able to carry it into the thoracic duct, and that will take it right into the venous system. So eventually all those fats will go into wherever it needs to go, the liver, wherever it needs to get digested further. We also have the fluid going into the spleen that's going to act like a bigger version of a lymph node. So it's going to cleanse that to make sure it can destroy the bacteria, viruses, cancer cells, and bring the fluid that's cleansed back into the venous system. The bone marrow itself is going to make, as you know, bone marrow makes all lymphocytes, right? Specifically, it's going to mature some of the lymphocytes to become B cells, but it also is going to put out the pre-T cells, right? So the B cells are going to come out of here, go into the bloodstream. It's also going to put out the lymphocytes that need to become T cells. We call them pre-T cells. They go into the bloodstream, but eventually those pre-T cells will go into the thymus. The thymusins will take those pre-T cells, then make them mature and become T cells. Now you got the T cells and the B cells into the bloodstream. B and T cells, we eventually go in all the lymphatic tissues, the lymph nodes, the spleen, the tonsils, and going to be sequestered there for their function to destroy any of the bacteria and viruses and stuff. And some of them will go back into the bloodstream, the B cells and T cells. But a lot of them will stay in there, okay? So that's basically the whole lymphatic system in a nutshell. That, and it's a pretty good summary of it all. Okay. So, any questions? All right. Again, I use this as my mascot for the lymphatic system because that's our stadium, right? The New York Giants Stadium, which is basically the same kind of setup that we talked about with the lymph nodes. Many afferent vessels, only a couple of efferent. They try and sequester the bacteria stuff so that the macrophages and lymphocytes can do their job. Okay?